Let's start by reviewing the things we already know about the derivative. The derivative of a function tells us the slope of the function at a particular x value. Since x often represents time, we can think of this slope as the rate of change of the function at a particular instant in time, so we call that instantaneous rate of change. Now we can easily find the slope of a secant line through 2 points of a function, but that just tells us the average rate of change. However, to find the slope at just 1 point, we need the slope of the tangent line. The problem? We can't find the slope with just 1 point. So solution number 1 is we use 2 points really close together to estimate the derivative. In other words, we're going to use the slope of a secant line to estimate the slope of the tangent line. So that looks something like this. We could take the red line is the secant line, the blue line is the tangent line, and the black line is the function. Okay, so this is just like one close-up little section of a function. And if we have 2 points and we move them closer together, so notice here we're at 2 and 2.1. So it's pretty close together. Here we're at 2 and 2.05, so much closer than before. And here we're at 2 and 2.01. And this is actually the example I used in class to have you do an estimate of the slope using a secant line, because we notice when we get this close, from 2 to 2.01, that the secant line and the tangent line are extremely close together. So we're going to get a very close estimate of the slope of the tangent line using the slope of the secant line. But we know that no matter how close we get, it's an approximation. Now, for all practical purposes, we could say 2.0000001, and we could get as close as we wanted to the actual slope. But there is a way to find the exact value of the slope, and that's using a limit. So a limit allows us to actually find the slope using just 1 point. So hypothetically, what we do is we say, here's our known point, and this is the point 2,1, but we're going to call it 2f of 2. In other words, this is the function value when x is 2. And then we're going to pick an unknown point and call it x f of x. And we're going to imagine sliding that point closer to the known point, sliding that unknown point closer to the known point. And we can think of this as slope, where here's our 2 y values, f of x and f of 2, and here's our 2 x values, x and 2, and we calculate the slope by subtracting the y values, f of x minus f of 2, over x minus 2. Now we know if we are taking the limit as x goes to 2, and we put 2 in for x here, we're going to have f of 2 minus f of 2 over x minus 2, and we're going to end up with 0 over 0. But thankfully, we have done some things with limits, and we know that it is still possible sometimes to find the limit in that case. And in this case, it will be possible. What we do is we substitute this entire function in for f of x, which is what we have here. So that's our y value. That's one of our y values. All this this expression in red represents our unknown y value. Then f of 2 is 1, so that is our known y value. And then here is our unknown and known x values, and we subtract those. And I'm not going to go through the process again, but if we do 3 minus 1 and get 2, and then we recognize that there's a common factor of x minus 2 in both the numerator and the denominator, we can divide out that common factor and take the limit and find the exact value of the derivative. So what's the issue with that? Well, it's a tedious process. It's going to be really tedious to use the limit definition for each specific point where we want to find the slope. And if we get into messier numbers, I've been giving you really easy, simple numbers to do where all the slopes always turn out to be a whole number and all that. But what if we have what if we have numbers that aren't as nice? That's going to really be tedious. So like what mathematicians always do, we're going to generalize the process and look for patterns in hopes of finding an easier way to do this. And there is an easier way. So let's go back and look at our first method of finding a derivative using the secant line. So I want to show you here once again, that's the little diagram that I showed on the previous part of the video. Notice here we have, and I'm going to underline these, we have 2.1, we have 2.05, and we have 2.01. And we're sliding that red point closer and closer to the black point in an effort to get a better and better approximation of the tangent line. So instead of thinking this as some unknown point x and some known point with 2, 1, and this is x, f of x, let's think of this as x plus 0.01. And this is x plus 0.05. And this is x plus 0.1. Okay? So if 2 is equal to x, then this is x plus 0.01, or x plus 0.1. This is x plus 0.05. This is x plus 0.01. And I guess to make this all look a little bit more similar, we'll just call this 0.1. Okay, so x plus 0.1. So what's happening is this little piece of extra that I'm adding on for the second point is getting smaller and smaller. And as this little extra that we add on gets closer and closer to 0, then we're going to have a secant line that's closer and closer to the tangent line. So let's think about calling that, let's use that little extra piece, and let's call it h. So we're going to generalize, and we're not going to use a known point. We're going to use two unknown points. We're going to use the point x, f of x, and we're going to use x plus h, f of x plus h. In other words, this is x plus a little bit more, like what we had before. So the difference between x and x plus h is just this little bit extra that we're adding, which is h. So what we want to find out as these 2 points slide closer together, what we want to find out is what happens when h gets close to 0. This is how we're going to find what's called the derivative function. Now we found the derivative as a single number, but now we're going to find the derivative as a function, and it has a special name. The derivative function is called f prime of x. So that little asterisk there is the prime, is what we call f prime of x. So we say f prime of x is the limit as h goes to 0 of f of x plus h, x plus a little bit more, minus f of x over x plus h minus x. And once again, you can probably figure out that if we put 0 in for h here and here, we're going to have f of x minus f of x over x minus x, and we're still going to get 0 over 0. So we still have that issue. We're still going to have to use a limit. But instead of getting just one particular number, we're going to get a function, and then we can use that function from now on to find derivatives. So the derivative function tells us the slope of f of x at any value of x. We use the limit definition to derive the function, but once we have the derivative function, we don't have to use the limit to calculate each derivative anymore. Pretty exciting. So next video, we're going to show how to do that with a couple of simple examples, and then we'll be able to derive the formula that is a really powerful tool in calculus.